Nico. So yeah, I have to connect what he said, because sometimes today and yesterday when I connected it to my PC to my HDMI, just my IntelliJ just froze my whole computer. And there is like this open bug which was created like updated an hour ago. So it will be fun if this will work or not, or if it will crash again. So it can be live. You can see this live. So, but I will try to give you a short introduction about Java 21 and virtual threads. So, short introduction about me. My name is Christian, as already mentioned. I'm a full-stack engineer, been doing Java for around 12 years now. Started then 7 years ago with TypeScript, Angular, and JavaScript. I do also some trainings on the side, and I really like to speak on conferences and try to share some knowledge I maybe have gained. So if you have any questions, of course, you can ask them at the end of the talk. You can also go to type.rocks/talkquestions. You can then just put in the questions if you'd like, or of course, at the end, we will have time for questions. So the topics we will talk about today is, we will go to like a trip from blocking to virtual threads. So we will start with a Spring Boot application. We will write it in blocking, and then we'll convert it to reactive and then to virtual threads, and we will see the advantages and disadvantages. So first, let's start with blocking. Quick show of hands, how many of you are still using like blocking APIs, like REST template or something like this in Spring Boot? Yeah, basically I'm also doing this mainly. Why? Because often you have like applications which don't need the performance of reactive. And it's much easier to understand the code in blocking APIs often, because with reactive you have like these different frameworks and all of that. So often it's good enough to use these blocking APIs, these REST template and so on. And this is why we often stay with these kinds of features. So some of us, me included, are sometimes still in the early days, and we say, well, this is still nice, we can work with this. Now, let me show you how such an application could look like. So we have here a new empty Spring Boot application, and we will just create a new controller here, and we want to have here get mapping for the speakers which are in this conference. But so let's say we have a REST controller, we have this request mapping here, we say API, and now what we can do here is we just say get mapping, and we want to do this for speakers. Now, we of course have to have a speaker endpoint, a speaker type, so we create a record, and say we have our list here, where we have our speaker, and we say get speakers. Now, of course, we could use a real HTTP service and query some results, but we want to have like do the control about the delay, because we want to test how a HTTP endpoint performs if we have like a delay of a second, for example. So we have an auto-wired here, and we say we have a fake HTTP service, and let's IntelliJ create this for us. Now we say this is a service. And what we now can just do is, let's go back here and we just say, well, we want to call this, we want to say fake HTTP service, and we say retrieve speakers. Blocking here so that we can differentiate between it. And now what we say is, we want to just return a list of speakers. So we have a list here, and we say we have a speaker list here. And we want to have just a fixed list of 10 speakers in this case. And we then create it like this. We say we want, for each of our index, we want to have our speaker. And we have a speaker name like this. So what we now can say is, of course I have to add this string here. So what we now can do is, we could, of course, just immediately return this in our retrieve speakers blocking. But we want to have like a delay, like in a real HTTP request. So what we say here is thread.sleep, and we say we want to sleep for like a second, like this HTTP request, which takes 1 second to return. So we then say sneaky throws like this, and then we just return our speakers. So we can now go back into our controller, and we now can just start our application. start our application, and we can now check how fast our application is. So we go into JMeter. JMeter is an application to test the performance of your endpoints. So what we say here is I have my API/speakers, which I call, and what I do here is I do use 1,000 concurrent users, which call this API. So let's get started. So we now see that we will spin up 1,000 threads, and we wait until these 1,000 threads are ready, and then we fire with all of them at the same time against our endpoint. And what we then can see is we have like our response graph where we can see what really happened here. So you have to wait, and now we can check our graph, and what you can see is it started at around 1.5 seconds, and it went up to around 4 seconds. And this is because we only have like a connection pool of the Tomcat server from around 200 threads. So then, because one request takes 1 second, we have to wait until this request is done, and if, when these 200 threads are busy, then we have to wait for even longer periods of time. So, but why don't we just create as many threads as we need? So let's check in our test how we can check this. So let's create a new test here. Let's call this just test. And what we now do is let's create 1,000 normal threads. So we have our thread here, thread list, and we say we have our int stream where we just create all our threads. So we have from 0 to 1,000. And for each one, we just say we want to have a new thread. And in there we can say we want to have a runnable, which we then will start. We say thread.sleep in there, and we say let's sleep for 20 seconds. This is because I want to show you something and I need some time to switch between the tabs. So now we say to list, and now we have our list ready, our threads ready. We now can start them. So we say for each, and we say thread start. Now, of course, we have to wait for all the threads to finish their work. So we say thread.join, like this. And we don't really care about what happens here if there is an error. And now what we do here is, let me switch to the terminal. I have here a function, count threads from Java. And we have 159 threads currently running. Now, let's see what happens if I start this. We can see now, this is now running. And if I check the threads now, it has created 1,000 threads. And this is a problem because one Java thread now creates one operating system thread. And this is exactly why it's not possible to create as many threads as we want. Because if we change this, for example, let's say to 1 million, what happens then is, if you run this test again, we get an out-of-memory exception pretty fast after around 4,000 threads. Well, why is this? The problem here is that one platform thread creates one operating system thread. Like the normal Java thread is like a small layer on top of an operating system thread. So, and this is why we can't use just an unlimited amount of threads, because one thread takes around 1 to 2 megabytes of RAM because it gets allocated. But the CPU usage here is only around 0.0001%. And to have a CPU usage of 100%, you would need like 1 million threads and 1 terabyte to 2 terabytes of memory. So maybe you think, well, but how do you, where do you take the CPU usage from? Well, how does our thread really use the CPU? In our case, it's we create this request, and this takes time from the CPU. The CPU needs to do stuff. We send it over, and during this time we are waiting, the CPU and the thread is idling. The thread is blocking, and the CPU can't do anything. And these are like 99.9% of the complete time we are doing this request response. But as soon as we get the response back, then the CPU is still busy again. So this is why some people said, yeah, well, we need more threads. But we have now seen, okay, this is not possible to get as many threads as we need. So now they were thinking, what could we do instead? And this is where they introduced the reactive pattern in Java, but also in other languages, to make this all reactive and to not block on these I/O applications and these I/O tasks. So let me show you how we can do the same stuff in reactive. So we go back here, and let's go into our controller here. Now what we do is basically we say we have here a get mapping, and we say we have speakers, but in this time let's call it async. Now what we can say here is, instead of returning a list, we say we have a completable future of a list of speaker, like this. We call this get speakers async. And what we now can do is we also call return fake HTTP service, retrieve speakers async, like this. Of course, we have to create this function. So IntelliJ already helps us. We need to return a completable future list. And now we can just use thread sleep to fake this delay, because we have to use completable future API. Now we say we use the supply async to just say we want to supply this value as with an async wrapper. Of course, normally this would be like a web client call from Spring Boot or like any other asynchronous web client. But in our example, we just return the speakers here. So, but now what we can do is to delay it, we can use a so-called delay executor. And we say we want to wait 1,000 milliseconds. And now we are also done with this. So we can go back in our code and just restart our application. So what we now will see is the speed difference between reactive ones and normal blocking operations. So let's go back into JMeter, remove everything so that we don't have wrong data here, and we now use speakers async. We just do exactly the same stuff we did prior to this. And you will now see what the speed differences are. And by the way, if you can't use Java 21, and I know there are many companies like they are still stuck with Java 8 or 11, and like even if you can't use Java 21, maybe this, what I will show you now, is also something which is helpful for you. Because when we now check the response time, we can see that we have a 1 second response time all the time, because this uses this reactive approach. So for every one of you who has still some problems with threads or blocking, you can still use this even in not Spring Boot applications, because this is completable future API from the JDK itself. So now this is really cool and this works fine, but let's say you want to make something more complex. Let's say you want to have for each speaker his talk. So we can say record, and we say we have a talk here, and let's call this here talk title. And now we have to get the speakers first, and then for each speaker get the talk from him. So we can say we have make a get mapping. We say /talks, and in the blocking approach, this is really easy. We just say we have a talk here, and we say get talks. Then first what we do is we get the speakers with the fake HTTP service retrieve speakers blocking. And then what we can do is we can say return speakers.map, and for each speaker we just call fake HTTP service retrieve talk, like this. We then pass in our speaker, and after that we say to list here. Now of course we have to implement this method, but we can do this really easy, which can just say this is a talk here. And now we say return new talk, and we have here talk from, and we have the speaker name. Now of course we also want to have a delay here. So what we can say is, let's say here thread.sleep of 500 milliseconds. Now we add this here. Now, the problem, of course, here is that this one here, even if you would not have the problem with the blocking, this one would take 1 second, and this here would take 10 times 500 milliseconds, which means 5 seconds. So, of course, you could use also a parallel stream here to make this faster. The problem, but is still that you still have an underlying thread pool, which also is blocked if there are too many requests. So how would you do this in asynchronous? You just say you have a get mapping here, and we call it talks async. We then say we have completable future of list of talk, and we say get talks async. Now, what do we need to do here is the difference between these two implementations, like here, these one with the talks and with the talks async, is that we can't breach this this reactivity chain. So what we need to do is we have our speakers async, and we say fake HTTP service retrieve speakers async, and then we have to say speakers async dot then, and then here you already can see there are so many different functions you can use. And when I first started using this, it was really hard to know which one I have to use to just normally map and call these other to basically switch map it to something else. And this is only Completable Future API, but there are, of course, Project Reactor, which also has like its own API. So each framework has like its own API. But we have to use then apply in this case. We then say we have our speakers. And these speakers now, for each of the speaker, we now have to do exactly the same as we did here. So we need to, like, we can take this. And now what we can do is we just copy this and we say we have our talks async or talk futures. And now what we say here is for each of the speakers, we call retrieve talk async. Now what is retrieve talk async? This now returns a completable future talk. And we now can basically copy this, what we have created already for our speakers, put it in there, and just replace the value we return. We don't want to return the speakers, but for each speaker, we want to return his talk. So we say async talk, and we have the speaker.name. So now you can see this works, but we are not done yet here, because this is still not what we want to return, because let's check what this really is. This is a list of completable future talk. It's like a list of completable futures, but we want to return a completable future list. So we have to wait for this. We have to say return talk futures, and we have to map over it and say we have a completable future, and we want to use where it is? Here, join to list. And now you can maybe see the difference between these two parts. The one really has just the business logic in there. The other one has so much boilerplate code around it. And this is basically what's the main problem is, that reactive code is hard to write, in my opinion at least, and you write a lot of unnecessary code just to satisfy these reactive constraints. Second one, it's also hard to read because you have many different implementations, and if you should switch projects and you, for example, have RxJava or have Reactor or have the Completable Future API, you have so many different ways of doing stuff. Third one, it's also not easy to test. If you, for example, are in Spring Boot with Reactor, you have to have your own like wrapper tools to work with these reactive stuff, with this asynchronous stuff. And it's also hard to debug, of course, and the compatibility is also not always given. So for example, you need to have compatible database drivers to even be reactive until the data, including the database, because otherwise, until at least at the database, it will block either way. And of course, and I really don't like that much because of these different implementations. I really hate that there are so many different ways of doing this stuff, because one likes, and all have other APIs. Like ones work with like just, or others work with just supply async. It's not really streamlined. So, but we see it's fast, but it's too complex. And so they went, the people from the JDK went back and said, well, okay, we need something else. But what was really the problem with these threats? Why did we go away from this blocking API? They were really thinking about this, and they were thinking about this for 5 years. They were developing Project Loom. Sometimes it was called Project Fiber. It was developed over 5 years. And they went back and they said, well, we need more threats. This is the only thing we can do to just be able to block a threat. So, but how many threats we need? Now we go full circle back, and we can see we need 1 million threats to be really happy. Why do we need 1 million threats and not only 500,000? Because if you have only 500,000, this is not really an alternative for reactive. Because with reactive, you have like 100% CPU usage, because you can really reuse all these threads and just use them if they are doing CPU work. So we need 1 million threads to really be a valid alternative. And they found the solution with the virtual threads. Simply explained is, virtual threads work on platform threads, but you don't have like a one-to-one mapping, you have an end-to-one mapping. You can have as many virtual threads which work on one so-called worker thread as you want. Because, this is how this works, we have a virtual thread. Let's say we are in our speaker example. We create our request, and then as soon as the request is sent, the virtual thread itself, the thread, tells by using a thing called continuation that it yields to the JVM, hey, I no longer need the worker thread. The worker thread is now free for other tasks to work. So what happens is the virtual thread gets put onto the heap and is unattached from the worker thread. And in this time, the worker thread is free to do other stuff. And this is also why the worker threads are pooled in a fork join pool. And we will, after that, we will see how many threads really are needed. But as soon as this response comes back from the server, we get a continuation. The virtual thread tells the JVM, I need another worker thread. So it connects to any available worker thread. It does not connect to the same one. It doesn't have to. It can, but it doesn't have to. It just takes one which is available. So let me now show you how this works in real life, in code. So before we go into the coding here of our application, let's go into this test here. So we have here this 1 million threads. Now the only thing I will change is I will say not new thread here, but there are new static functions on the thread. You can use thread.offPlatform. This is exactly the same as prior. This is like the normal thread you know. But you can also use offVirtual. So let's change this. Now, of course, this is no longer in there. We can say unstarted. And now we have exactly the same behavior, but with a virtual thread. But you can see it's still a normal thread, because virtual thread extends from the normal thread. And now let's go back in here in our count. We can see we have 154 threads running. Now let's start this here and start 1 million threads. And we are starting this. The first thing we see is we don't get an out-of-memory exception. And now let's check, and we can see only 42 threads got created, because we see that these 1 million threads don't get created in their operating system, but they are like in the JVM itself. And they only need like in the kilobytes of memory, while the platform threads need around 1 to 2 megabytes of memory. The virtual threads only need in the kilobytes. So you can create like 1,000 more threads easily, 1,000 times more threads easily. So we can see here after it's done, it's now again back to these normal threads. Now, let me show you how these really work. So what we say here is, we say if I is 0, because we want to like take a look into one specific thread. We say here we have our thread.current thread, and we print out our value. And what we then do is, let's say we have a thread.sleep of, let's say, 20 milliseconds. Now the interesting part is, let me rerun this. We will see what happens with this thread. We have, of course, to copy this, otherwise it's not really that fun. So I just restart this, and we can see here, it's the same thread every time. It's thread 22, 22, and also 22 here. But it's running on worker 9, 6, and 2 here. So it switches each time it blocks to another thread which is currently available. And how is this really? How is this working? So let me show you. Let's go into the thread clause. This is like available since Java 1. And I think this was not touched until Java 1 either. But let's go in here. We can see this if-else block. They've put in everywhere you're using threads, everywhere, in all the NIO stuff, everywhere you're using threads, they've updated the code so that it's working with virtual threads. So when you look at the pull request of the JDK to change this to allow virtual threads, there were over 100,000 changes in this pull request. And it's clear because you can't just change it in one on one position. Everything, everywhere has to work together. So they really did an awesome job, and they introduced it in Java 19 as a preview feature, and now it's really available in 21. So this is not like preview, but this is really, you can use it right now. But now let's use this in our application. And now really the cool part is, I'm using here Spring Boot 3.2 release candidate, and I'm using it because this way I can just go into my application properties and I say Spring Threads virtual enabled, and I say true here. If I would be in version 3.1.5, which is the newest one, you would have to override the Tomcat executor service, because Tomcat, as already mentioned, they pool their threads, and you would have to override it, and you could just go in there and create your own bean, and you could then say executors.new virtual thread per task, because you should never pool your virtual threads. It's like one usage type of thing. You use it once and then you throw it away. This is also why you shouldn't use it with parallel streams, because you should not pool these virtual threads. But I will show you later how this can be done differently. But let's just say we have enabled here these virtual threads. And you could do the same thing with the executor service. But we have seen I've changed nothing in the code. Now let's just restart the application with the virtual threads enabled. So we all still know that if I call the speakers API, the speakers endpoint with around 1,000 threads parallel, then we got like times from 1.5 to 4 seconds. Now let's see what happens here. We go back here, let's delete everything so that we don't get wrong data. And now I call my speakers endpoint again. We see we now spin up our 1,000 threads. And now we were waiting, and then it will again do exactly the same thing. But now what happens is, because we are having virtual threads, we have so much more threads available to do the stuff we did prior with only around 200 threads. Now what we can see here, I go to this to the graph, and it's 1 second throughput. So it can't be any faster because we have entered this delay of 1 second. But what happens here basically is really easy to understand, because we go in here, and this thread sleep is basically what happens if you call the REST endpoint with the REST template. And as soon as this blocking operation is triggered, the virtual thread will detach from the worker, and now the worker thread can do other stuff. And this is also done with like 40 threads, so you don't need even these 200 pooled threads from Tomcat, but like 40 threads are enough for a huge amount of throughput. So, but let me now show you what you can do with this get talks here. Because the problem here still remains that this takes 1 second, but this would still take 5 seconds. So I've told you don't use parallel streams, because you can use another feature they have introduced. This feature is currently in preview and will be final in Java 22, but you can use so-called structured task scopes. Let me show you how this works. We have a try block here, and we say this is a structured task scope. We say we want to pass in which elements we want to call blocking with it. And now, what is a structured task scope? You can think of it like an executor service. And what you can do with this, let's say we just can copy this. We have here then our talk tasks, and we put this in here. Now, this is now exactly the same, but what we now have to do, of course, is we have to send this retrieve talk by using our scope. So what we do here is we wrap this in a so-called scope.fork. So this takes a runnable, and we just wrap this in there. And what happens here with this fork is we send this task, and the scope will create a new virtual thread for it. And this is like basically, it looks a little bit similar to the completable future. But what now the cool part about this is we can now say scope.join, and you can see here you have also a join until, so that you don't have to wait until the end of day, but you can just let us use join like this. So what we now can say after this join waits for all the tasks we've sent to our structured task scope to finish. And it can either finish in success or in failure. Each task has a state which is either unavailable, success, or failure. So you can even check the result and so on. But let's now think this is just a normal, this will work. So we say we have our talk tasks, we say here map, and we can here also, access the subtask and say get to get all the results from our subtasks. Now, let's make it like this. So now let's restart the application. Now, what we can do here is, let's go back into JMeter. We again remove everything we have here, and now we use here /talks. Now, what we are hoping for is that we have exactly 1.5 seconds of throughput, because there's 1 second of the speakers and half a second for each of the talks. But because it's run concurrently, we don't have to wait like these 6 seconds. So we're waiting these 10 seconds to run it. And after this now, let's check the response time. And we can see it's 1.5 seconds, because we've used this structured task scope. Now, you may be, and I was thinking the same, when you see this, you think, yeah, well, this is nice, but you also have like to call this join each time and to map over this. It's not really that nice, and it's also some boilerplate. This is why you can create your own structured task scope. How can you do this? Well, you say you have your own class. You say, let's call this talk scope, and we extend the structured task scope like this. We say this is a talk. And now, the cool part about this is you have a function here, handle complete. So each time a subtask completes, this function is called. And so here, for example, you can also collect all the errors, because you can check if this subtask was successful or had an error. So you could say subtask.state here, and the state is either successful or error in this case. But what we want to do here is we want to collect all these talks and then just return them. So we can say, let's use a queue. And I'm using a queue here because to have a concurrent collection. So we have our talks here. Let's make this private. And we can now say we have a new concurrent linked queue. And what we now say here is we just say talks.add, and we say subtask, and we get the value of it. And what we now can just say is we want to just say get talks here and return our talks. But what we have to do prior to this, of course, is we have to say we want to join it. So we want to say, if we call get talks, please wait for all the tasks to finish, because otherwise we would not get all the responses we wanted. There is also a method on there, ensure owner and joined. So this you can call to check if the user of this object currently really is the owner and has joined all the subtasks. So like this. And now this is already what we had to do to create our talk scope, and everywhere you can now reuse it. So, but now let's go back here. And what we now can do is we can say, well, this is no longer a structured task scope, but by the way, there are also implemented ones already for shutdown on failure and shutdown on success. So for example, if you want to shut down if there is one error, then you can use this one, or as soon as there is one successful result, then you can use the other one. But let's just say we want to use ours, of course, and we say we have our talk scope like this. And now what we can do is we don't need this anymore. We also don't need this to list anymore. We can change this to for each, because we want to just fire and forget, basically. This join we don't need anymore. And now we can just use scope.getTalks like this. Of course, this is not a list anymore, but a collection. But you can see here, this is like 4 lines of code, and you wrapped all the complexity in like the structured task scope. And also, if you think about this, this is really easy testable. So you don't have any like asynchronous stuff in here. It's all still blocking API. If you think here, this retrieve talk still takes a speaker and returns a talk. So you can test it really easy in your code. So let me show you that this still works. We just rerun this, and for the last time of today, we will just call this again. So we do basically the same here with the talks. We just call it. And we now see again the 10 seconds uptime. And we'll then see it's exactly the same as before. So this way you can wrap your structured task scope and create like your own ones. There are also many also libraries for this. For example, if you have like want to collect a collection, there is like a collection task scope and so on from other libraries, I think from Apache, which you can also use. But now it's done, and we can see that this is still 1.5 seconds because nothing really changed. We just used our own structured task scope. So let me go back to the presentation. So we have some restrictions to this, but one important thing which is not a restriction is thread locals. You can still use your thread locals as before because it's really important to say normal users should not know if they're using virtual threads or normal threads. It's like really there are just, you can use every normal, if you like have a highly concurrent tool currently running in pure JDK, you can just change from normal threads to virtual threads, and you should not see any difference, but the speed improvement, of course. Also, you can of course use thread locals, but Tomcat, for example, had a problem with synchronized blocks because they had many synchronized blocks, and in there you cannot unattach the virtual thread from the worker, so it's like pinned. So if you have a synchronized block which does heavy I/O work, so if you don't go to the synchronized block fast, they changed all the synchronized blocks to reentrant locks. Reentrant locks are like just the Java equivalent of the synchronized, and they have implemented there also the virtual thread handling. And so Tomcat changed it, and it worked just fine. And I think if Tomcat, with their real complex stuff, can do this, then in 99.9% of times you can also do this easily. Second one is also something which not happens that often, native calls. If you do calls into C code, in C you can access the memory, the memory addresses. And so there it's also not possible to remove the virtual thread from the platform because this would mess with the addresses. And the third restriction, and I think this should be clear, but it's like sometimes we forget why we use virtual threads. You have no speed improvements if you are running a thread with a CPU-heavy task, because virtual threads are then useful if you have I/O-heavy tasks, because virtual threads then get attached on the I/O tasks. But if you have CPU-heavy tasks, like you are calculating something, then of course the thread is busy and it will not unattach. So let's go to the conclusion. Now, first thing is, in my opinion, you can really make blocking great again, and it's a real alternative to reactive. And what also is really cool is it's an easy proof of concept for you to do, because let's say you have a problem with the performance. If you would have to change everything to reactive, you would have to really change everything to see if what's the speed improvement. But with these virtual threads, you can just switch on a flag or change to another executor service and then see if first your application still runs, and second one, how the speed improvement is. So it's a really easy and a quick fix and a quick win. Third one, it's done in the JDK. So you have like one implementation. Of course, there will be like some wrapper libraries which make some stuff easier, but you don't have like 3 or 4 even 100 different implementations of reactive stuff. You have like one implementation in the JDK which you can then extend on. And maybe you've also seen it's much less boilerplate. You have really simple patterns which you can use with these structured task scopes, but often if you just have like, you take a request and send something back immediately, you don't even need the structured task scope, like we have seen with the speaker list. So yeah, in the timeline, we are now like in Java 21, and we are here in my opinion, it's like this was a huge milestone for Java. It did take them 5 years to achieve this, and I think really they had done so much work to achieve what we currently have, and to make it so easy for the users to just change without having the headache to like having to work with this thread stuff themselves. So we don't know what the future brings us, what maybe reactive will come back with something else. Also, it's important to say I'm really not against reactive, because as a full stack developer, I'm often working in the front end basically only with reactive, but I also see really the advantages of like this blocking stuff, of like this not like this nested stuff, but like you have it like also in the front end with async await, you can write it in one block and don't have to nest everything. So I really like this too. Yeah, are there any questions? Yeah?
Thanks. Is there a way to capture the continuation and work with it?
Yeah, you can, but they made it a little bit hard because they don't want you to. But it's a private, it's private in the JDK, but you can like add some flags when you start a JDK, and then you can work with the continuation class. It works, but you have to work your way to it. Yeah, but you can do it. You can also do like work with the thread pool and handle it yourself, I think. But it's like they really made it hard to achieve it. But you can do it, of course.